Okay. So welcome everyone, and welcome to our speaker from Canada, Matthew Kennedy, non-commutative convexity. Please, Matthew.
Yes, thanks a lot for the invitation to speak, and thanks in particular for accommodating my schedule and moving the talk back a couple hours. I really appreciate that. So I'm going to be talking about, so this is joint work that's taken place over a series of about 3 or 4 papers with several different co-authors. So Davidson, Kim and Manor were students of mine, and Shamovich was a postdoc of mine who's now at Ben Gurion in Israel. And the starting point for my talk is something that everybody in non-commutative geometry is very familiar with, of course. So I want to start with the dual equivalence between the category of unital commutative C-star algebras and compact Hausdorff spaces with, so the space, or the category of Hausdorff spaces we equipped with continuous maps, commutative C-star algebras with unital star homomorphisms. And so I don't actually want to talk about this. I want to talk about something that's analogous to this, that's very important, probably not quite as well known. So first of all, a definition. So a function system, a unital function system, or something sometimes known as an Archimedean order unit space. This is a closed unital self-adjoint subspace of a commutative C-star algebra. And there's an important theorem of Cadison, which says that every unital function system, if I take C to be its state space, then the function system is unitally order isomorphic to the function system of continuous affine functions on C. And so this gives us an equivalence of categories between function systems where the morphisms are unital order homomorphisms and compact convex sets with continuous affine maps as morphisms. And so this K on the bottom right corner should be a C. So the subject of my talk today is a non-commutative analog of this correspondence between function systems and compact convex sets. So this idea goes back a long ways. It goes back at least to the work of Arvidsson in his famous paper, Subalgebras of C-star algebras from 1969. So just to begin, I'm going to introduce some notation. So a unital operator system, this is a non-commutative analog of a function system where we replace the commutative C-star algebra with an arbitrary C-star algebra. So a unital operator system is a closed unital self-adjoint subspace of an arbitrary C-star algebra, arbitrary unital C-star algebra. And so as I said, in 1969, Arvidsson considered operator systems really as non-commutative analogs of function systems. So he was particularly interested in proving an analog of the Hahn-Bonnet extension theorem, the Krein extension theorem, which he accomplished, and we now know as Arvidsson's extension theorem. And this is the context in which he proved his theorem. In addition, in this paper, he conjectured the existence of an analog of the Choquet boundary for an operator system. So the Choquet boundary is a sort of convexity theoretic notion that arises when you're studying classical function algebras. And I'll come back to this in a little while. So the way that I like to see this is Arvidsson was really working on the side of the operator systems. He was working on sort of the algebraic side of things. In 1981, Wittstock started to study the dual side, and in particular, he introduced a notion of matrix convex set. And there were quite a few developments around this, which I'm going to pass over in the interest of time. So I'm just going to highlight the developments that were important specifically for my talk today. So in 1987, Efros and Winkler was a student of Efros, returned to this notion of a matrix convex set, and they were able to establish analogs of the, or an analog rather, of the Hahn-Banach extension theorem for matrix convex sets. And this is actually quite a deep result. In 1999, Webster and Winkler, they established, so these are both students of of Efros, established the fact that these matrix convex sets, these are actually the dual objects in the sense of dual equivalence of categories to the category of matrix convex sets. And in 2007, and then subsequently 2015, so Arvidsson had conjectured the existence of something that he called the non-commutative Choquet boundary of an operator system. He was finally able to establish the existence of the Choquet boundary in the separable setting in 2007. And Ken Davidson and I were able to finish things off and show that the existence in general of this object in 2015. Okay. So there have been a lot of, even since 2015, there's been a lot of development in this area. Of course, in the last 20 years, there's been a ton of developments, major developments in the theory of operator spaces and operator systems, and even going back earlier than that. One thing that's been quite interesting more recently, there have been a lot of interesting examples arising of matrix convex sets. So on the convex or the geometric side of things, sort of establishing in my mind that these dual objects, they are actually, there is actually some value to looking at things from this perspective. And in particular, I'm thinking of the work of Helton and McCullough in non-commutative real algebraic geometry and in optimization. However, there are some technical issues as well with matrix convexity. The primary problem I'm thinking of is the fact that you can prove that there are lots of examples of matrix convex sets where there's just no good notion of extreme point. And so much of classical convexity theory relies on having a robust notion of extreme point that this causes a major difficulty in the theory. So what I'm going to talk about today is I'm going to talk about how, with a refined notion of what we call a non-commutative convex set or an NC convex set, this gives an appropriate dual object to operator systems in the sense that there are good notions of extreme points. You maintain this categorical equivalence with operator systems, both in the unital and the non-unital case. There's a very, I think, interesting notion of non-commutative function theory, which really parallels the development of non-commutative free analysis or non-commutative holomorphic functions, which has been happening in free probability and more generally non-commutative complex analysis. And then finally, there's a good notion, I think, of non-commutative Choquet theory, which Ken and I developed about a year or two ago. So I'll talk about this, and I'll finish off with some applications to non-commutative dynamics, which I think are quite interesting. Okay. So just to start with basics, I'm going to talk about the notion of a non-commutative convex set. And the motivation here is we begin with a unital operator system. So remember, this is a closed self-adjoint unital subspace of a C-star algebra. And we talk about the non-commutative state space, which is a generalization of the state space. So if we think of the state space of a C-star algebra or an operator system as a set of maps from the operator system into the complex numbers that are unital and positive, well, we know that they're also completely positive. So for n greater than or equal to 1, we consider instead the set of unital completely positive maps from the operator system into the n by n matrices. And here we're allowing n to actually be an infinite cardinal. Not only allowing, we're requiring that we take n to be a suitable infinite cardinal. So how big does this cardinal have to be? Well, there's a precise sense in which we can sort of specify how big it has to be. And this has to do with the extreme points that I'm going to discuss in a little bit. But for now, operator system is separable, then I can say that it suffices to take Aleph naught as the largest cardinal we need to consider. and by the way, that should say the maps here should be from S into Mn, not A into Mn. Yeah, thank you. So this refines the notion of a matrix convex set, which I mentioned earlier, because a matrix convex set, and so the matrix state space of an operator system, this is what we get if we take n finite. So we take n over the natural numbers. This is seems to be a very minor point, but it actually turns out to be extremely important, because none of the things that I mentioned in my previous slide, none of the things I'm going to be talking about today actually work if you don't consider, if you don't allow in general these points at infinity. And the main—
What is exactly the definition of M for Aleph 0? Is it operators in Hilbert space?
That's right. This is just the L2 if you like in that case. You can identify M with the L2.
Matthew, there is a small point in the chart. I think somebody's asking, should it
right.
be X from S?
Yeah, so this A here should be an S.
Okay.
That's the typo.
Okay.
Thank you.
Thanks.
So a thing to observe here is that each of these KNs is compact if we consider it in the point weak star topology. And so this is just the natural generalization of the weak star topology on the state space of a C-star algebra. And moreover, it's closed under what we think of as non-commutative convex combinations. So namely, we take this sum over alpha I star, xi, alpha I, where xi are points in k and I, and alpha I are matrices of a suitable size, or operators of a suitable size, because we're allowing things to be infinite, where these coefficients, these alpha I star, alpha I's, these add up to 1. So this notion of a non-commutative convex combination has been something that has arisen many different times in operator algebras, many different settings. It's a very natural notion. Excuse me. And this motivates the definition more generally of a compact non-commutative convex set. So this is a graded set K, just like in the previous definition of this non-commutative state space. The base space typically will be a dual operator space. For example, it will be the dual of an operator system, because we want to have a nice topology that makes each of these KNs compact. And we require, in addition, that K is closed under non-commutative convex combinations of the type that I mentioned. So of course, the NC state space of an operator system is an example. And so here's a nice example that we like to, or I like to think of as a non-commutative analog of the circle, the complex unit circle. So this is the non-commutative D ball. So this consists of row contractions, so D tuples of operators, satisfying the condition that the norm of the row of these operators is less than or equal to 1. So we call these row contractions. And so if I let O of D be the Kuntz algebra, so the Kuntz algebra with generators V1 to VD, so Kuntz isometries satisfying the Kuntz relations. Vi star Vj is delta Ij, and then the range of the Vi's adds up to 1. Then it turns out that this set K, this is actually the non-commutative state space of what's often called the Kuntz operator system, spanned by the identity, the generators of the Kuntz algebra, and their adjoints. Okay. And I'm going to return to this example in a few slides. More generally, as I mentioned, there are a lot of nice examples coming from, for example, from non-commutative real algebraic geometry. So there are examples arising in the theory of nice and interesting matrix convex sets where maybe the sort of dual side isn't as well understood. And I'm going to return to this point. Okay. So having a notion of non-commutative convex set and thinking about the classical setting where we have a compact convex set, one of the most important things that we do with compact convex sets is we consider the functions on them. And we want to do the same thing here. And the observation here is that if I take a unital operator system with NC state space K, then I can think of elements in my operator system as functions on K in a very natural way. And this mirrors what happens in the classical setting. So I'm going to let A hat be the evaluation function corresponding to A. So namely, A hat takes a point X in this NC state space, turns things around, and evaluates A at X. Now notice that this is a function from K into the matrices of an appropriate size. And it satisfies, it's not too hard to see if you sit down and think about this for a minute, satisfies the following properties. So first of all, it's graded in the sense that it sends elements in Kn into the n by n matrices, right? Because by definition, Kn consists of maps into Mn. It respects direct sums. If I take a direct sum of elements in these Kns, so direct sums of UCP maps are UCP maps. And A hat respects direct sums in the sense that, well, in the sense that I've written down here for number 2. And the third thing that's important is that A hat is equivariant with respect to isometries. And what this really says is that A hat respects the structure of the NC convex set K. So it sends, this turns out to be equivalent to the statement that A hat sends NC convex combinations to appropriate NC convex combinations. And this brings us to motivates the definition of an NC convex function more generally. So this is a function defined on an NC convex set K. It takes K to matrices of appropriate sizes. So Kn, elements in Kn get sent to matrices in Mn. Respects direct sums, and it's equivariant in an appropriate sense. So if I want an analog of an affine function, okay, then I want something that respects NC convex combinations. And that means that it should be equivariant with respect to isometries, like the elements in the previous slide were. But more generally, it turns out that I want to consider elements that are equivariant with respect to unitaries, which is a weaker condition because every isometry, or sorry, every unitary rather, is of course an isometry. Okay. So this turns out to be exactly the distinction in the non-commutative setting between functions that are affine and general functions. Okay? And if you're familiar with the notion of a non-commutative holomorphic function, considered first by Taylor in 1973, and then by Voiculescu in his theory of free analysis in 2000, and by many other people subsequently, this is very, very similar to that definition. In fact, if you replace this condition of unitary equivariance with a similar condition using similarity of invertible operators, that is actually basically the definition of an NC holomorphic function. So there's something going on here which is very interesting. What this is saying is essentially that in the case of, well, it's saying that NC holomorphic functions will be examples often of NC functions in this sense. Okay. So we have a notion now of a continuous NC function. I'm going to give you an example on this slide. This set of NC functions, they compose in the sense that I can multiply them together pointwise, because the image of a point X lives in Mn, and there's a nice multiplication in Mn. So there's a question: are these coefficients alpha I in these NC convex combinations, are they related to cross operators in quantum information theory for quantum channels? And the answer is yes, absolutely. Those are examples of taking NC convex combinations of, if you like, of maps or completely positive maps. Okay, so I can consider, as I was saying, the continuous NC functions. They form a nice algebra. In fact, they form a C-star algebra under pointwise multiplication. And the set of affine NC functions is a sub-operator system of this C-star algebra, a unital sub-operator system. And we want to think of elements in C of K, and this notation is chosen to be suggestive of what happens in the classical setting. We want to think of these elements in C of K as uniform limits of non-commutative star polynomials in the A of K. So what this looks like is if I take, for example, 3 elements, A1, A2, A3 in A of K, and I define F to be the non-commutative polynomial, actually the non-commutative star polynomial, given on the screen, then the way that F is defined on points X is, remember, I'm defining F by pointwise multiplication. So this is what the first line, F of X, this is sort of the functional, if you like, notation. And the second line is what's underlying this definition. Remember, is that these X's, if, for example, if K is the NC state space of an operator system, these X's are really UCP maps, right? UCP maps on the operator system. And, excuse me. And what I'm doing is I'm composing UCP maps and then multiplying. Okay. And it turns out that we can really think of this C-star algebra C of K as this uniform limits of these non-commutative star polynomials. So this is a kind of, if you like, a kind of non-commutative Stone-Weierstrass theorem in a very special case. It turns out that, that this algebra of continuous functions, this is exactly the C-star algebra generated by these affine NC functions A of K. And we can identify this, if you're familiar with the notion of the universal C-star cover of an operator system. So this is an analog for operator systems of the universal C-star algebra. Then we can identify C of K with this algebra. Okay. So the universal property here is that every UCP map of the operator system extends to a star homomorphism of this universal or maximal C-star cover. And it turns out that the bidual of the C-star algebra, this consists exactly of the NC functions that are bounded in an appropriate sense, basically just uniformly bounded over the levels Kn. And the proof of this result uses a fairly deep result of Takasaki and Bechsteller from the 1960s, which is so Takasaki was after a non-commutative analog of Gelfand's representation theorem. So he was able to prove this in the separable case, and later Bechsteller was able to prove this in complete generality. And their results really underlie the proof of this kind of Stone-Weierstrass type theorem here. This turns out to be a very important result because it sort of it's what holds our theory together. And in particular, it allows us to excuse me, to obtain some nice results about dual equivalence of operator systems and the operator system of affine functions on a compact convex or a compact NC convex set K. So specifically, so I mentioned already that Webster and Winkler proved a dual equivalence for the case of matrix convex sets. And it essentially follows from their result that we get a dual equivalence for compact NC convex sets. So specifically, an operator system, a unital operator system with NC state space K is unitally completely order isomorphic to the operator system of continuous affine NC functions on K. And this gives us a dual equivalence of categories. Every operator system of the form A of K corresponds to its NC state space K under this dual equivalence. Okay. So this is in the unital setting. It's also interesting to consider the non-unital setting. So this is something that was done originally by Werner in 2002, and then more recently by Kahn, excuse me, and Van Swielekom in 2020. And this actually caught my eye, as well as the eye of a couple of my PhD students, because we realized that nobody had really worked out the non-unital case of this dual equivalence that I just mentioned. And this is something we recently decided to do and turned out to be quite interesting. So in order to talk about the dual equivalence in non-unital case, I need to tell you what a non-unital operator system is. So a non-unital operator system, in the sense of the people I mentioned above, this is a closed self-adjoint subspace of a C-star algebra. Okay? So in particular, not necessarily unital. It's equivalent to saying that we can embed it in an appropriate sense as a self-adjoint subspace of some B of H. And the right replacement for the NC state space in this context is the NC quasi-state space, which is an analog of the usual quasi-state space of a C-star algebra. So this is the set of maps from, and then again, this A here should be an S. This is the set of maps from S into a set of matrices in appropriate size, or more generally, the operators, which I'm denoting by Mn, acting on a Hilbert space of dimension n. These are the maps that are completely contractive and completely positive. The NC quasi-state space, I also want to keep track of 0. So I want to think of this as a pair consisting of these NC quasi-states along with a distinguished point 0. And now the 0 map, we identify 0 at the scalar 0, and this lives in K1. Okay. And there's a fundamental difficulty in the non-unital case. So in the unital case, remember, every compact NC convex set corresponds to the NC state space of an operator system. This is no longer true in the non-unital case. Things get a little bit delicate. And so we say that a pair consisting of an compact NC convex set and a distinguished point Z in K1, so on the first level, we say that this pair is a pointed compact NC convex set if it's the NC quasi-state space of the operator system of NC affine functions, continuous NC affine functions that vanish at Z. Okay. Now it's possible to write down sort of more geometric, or if you like, a more intrinsic characterization of when such a pair is pointed in this sense. But the key point is that we get, with this definition, we get a nice dual equivalence between the category of generalized operator systems and pointed compact NC convex sets. And even in the classical sort of commutative case, so if you like non-unital function system, it seems that this theory hadn't been worked out. And so some of these things, I'm sure that people were sort of aware of how you could maybe formulate such a theory, but I haven't been able to find it written down anywhere. But you get a nice correspondence between operator systems and pointed compact NC convex sets in this sense. And this allows us to essentially generalize most of the results that I'm going to be talking about today to the non-unital case. In some cases with some extra work, but the key point is that things work out in the non-unital setting for the most part. Okay. Now I also quickly want to mention extreme points in the context of NC convexity. So this turns out to be a major sticking point. As I mentioned, the theory of matrix convex sets, one of the sort of drawbacks of that theory is the fact that you can prove that there often are not going to be sufficiently many extreme points in any appropriate sense for a matrix convex set. It's really important to have these points at infinity, and things like for example, notion of a continuous NC convex function. It doesn't work so well if you don't look at these points at infinity. So there are examples of, it's easy to actually write down an example of a function, an NC function, that's continuous in all the finite levels, but it's very, very discontinuous on, say, the first infinite level. And this really makes it clear and essential that you need to sort of consider these infinite levels as well. Okay, and the point I want to make here is that there is, if you allow for these points at infinity, there is a very robust natural notion of extreme point for a compact NC convex set. And moreover, there's a nice analog of the Krein-Milman theorem in this setting. So a compact NC-convex set is the closed NC-convex hull of its extreme points. Now, this turns out to be a very difficult theorem to establish. It relies on the existence of what Arvidsson called boundary representations of an operator system. So remember, Arvidsson conjectured in 1969 a non-commutative analog of the Choquet boundary for an arbitrary operator system. It wasn't until 2007 that he was actually able to establish this result in the separable setting. And then later in 2015, Ken Davidson and I were able to establish this more generally. But it's non-trivial. There's a very, it's a difficult proof. And this is really dual to the Krein-Milman theorem in the sense that the existence of these boundary representations is equivalent to the existence of extreme points for compact NC-convex sets. So more recently in 2019, Ken and I published a paper we called Noncommutative Choquet theory, and we give a new proof of existence of extreme points. So from this perspective of compact NC-convex sets, which gives, of course, another proof of the existence of boundary representations in Arvidsson's sense. So let me give you an example. If we go back to this non-commutative D-ball that I mentioned earlier, remember this is the NC state space of this Kuntz operator system. And it turns out that the extreme points of this set K, these are the irreducible Kuntz isometries in the sense that they're Kuntz isometries satisfying the Kuntz relations for the Kuntz algebra. They're irreducible in the sense that there's no non-trivial common or joint invariant subspace. Equivalently, these are exactly the points that give rise to irreducible representations of the Kuntz algebra, OD. And what I want to point out is that we can identify these extreme points with a subset, with actually the whole space of irreducible representations of OD. And more generally, for an arbitrary operator system with NC state space K, the set of extreme points of K can be identified with a subset of the space of irreducible representations of the C star algebra generated by A. And often, most of the time, in fact, it's not the case that they're sort of a nice subset. They're typically never equal to the entire space of irreducible representations. Typically, it's a very complicated subset of irreducible representations. So there's a question in the chat. Should N be D in the Kuntz? Yes, N should be D. Yeah, there should be D generators here, generating the Kuntz algebra OD. Thank you.
There was a previous question actually, which I missed. Are these alpha related to Krauss operators for CP-TP maps?
Yeah, so I did address that, and it is true that you can view Krauss operators. So the Krauss decomposition of a quantum channel, you can view that as a kind of NC convex combination. That's certainly true. Yeah, thank you. So to talk about applications, I want to quickly review some notions from classical Choquet theory. So what is classical Choquet theory? People typically have seen the Bishop-Deleuze integral representation theorem. I think more generally of classical Choquet theory is it's really the study of a compact convex set C using the duality with the function system A of C, continuous affine functions on C, and then the relationship between A of C and the continuous functions on C. So let me review the integral representation theorem of Bishop and Deleuze. So this says that if I have a compact convex set and a point, say X in my compact convex set, then if I have a probability measure on my set C with the property that if I view my probability measure as a state on the space of continuous functions on C, if the barycenter of this probability measure in the sense, so the barycenter here means the restriction to the continuous affine functions. If this is the point evaluation at X, and notice that it's always a point evaluation at some point, but if it's a point evaluation at X, we say that mu represents X. And what this really suggests means is that x can be decomposed as an integral against mu of points in the space C. So this is a kind of generalized notion of a convex combination. We're thinking of measures here as convex combinations. We're saying x can be written as a convex combination of points given by points in the support of this measure mu. So notice that if mu is finitely supported, this is literally just the convex combination. And Choquet and Bishop and Deleuze proved that it's always possible to find a representing measure for a point in C. You can always find a measure representing it supported on the set of extreme points. This is like saying that every point can be written in an appropriate sense as a convex combination of extreme points in our space. So this is an analog of Cartier-Dore's theorem from finite dimensions. And one of the key contributions of Bishop and Deleuze is that you can detect this property of being supported on extreme points in an order theoretic way. So specifically, there's a notion of Choquet order. So Choquet order on the set of probability measures is defined by saying that mu is dominated by nu if mu of f is dominated by nu of f for all continuous convex functions f on C. So this is called the Choquet order. And maximality in the Choquet order it implies that your measure is supported on a set of extreme points in an appropriate sense. So if we're in the metrizable setting, it literally means you're supported on the set of extreme points. If I'm in the non-metrizable setting, it could be the case that my extreme points are not a Borel set. And I have to be a little bit more careful about what I mean. But there is a notion of being supported that works well even in the non-metrizable setting. And so a compact convex set is a Choquet simplex or a simplex if there's a unique representing measure for each point that's maximal in the Choquet order, equivalently supported on the set of extreme points. So this is like saying C is a simplex if there's a unique way of writing every point in terms of extreme points. And in finite dimensions, because this is really Cartier-Dore's theorem, this is literally what it means to be a simplex. It means that every point can be expressed uniquely as a convex combination of extreme points. And we have a very good understanding of simplices in finite dimensions. So the 0 simplex is a point. The 1 simplex is a line. More generally, we like to think of simplices as triangles or generalizations of triangles, because in 2 dimensions, the 2 simplex is literally a triangle. And every triangle is homeomorphic, afffinitely homeomorphic to your favorite triangle. And then more generally, there's a 3 simplex or tetrahedron, and so on. And so we think of, so in infinite dimensions, simplices can be very complicated, but also very interesting. And we think of these as generalized triangles. And it's this property of having unique maximal representing measures that I want to single out. And I want to apply this. I want to talk about several applications of simplices that I'm then going to mention, generalizations of in the non-commutative setting. So the first application is giving a characterization of state spaces of unital commutative C-star algebras. So how do you recognize that a compact convex set is the state space of a C-star algebra? Well, there's a nice way to do this in the classical setting. Say that C is a Bauer simplex if it's a simplex with the property that its extreme points are closed. Okay. And Bauer observed that a function system, A of C, is actually order isomorphic to a C-star algebra, which is a unital C-star algebra, if and only if C is a Bauer simplex. What this really said, so in finite dimensions, the D simplex is unique up to affine homeomorphism. And this says that in finite dimensions, there's a unique commutative C-star algebra of each dimension. Something, of course, we already knew. I'm not claiming this is so deep. But more generally, C is a Bauer simplex if and only if it's affinely homeomorphic to the state space of, or sorry, to the space rather, probability measures on a compact Hausdorff space. So K is the state space of C of X, in other words. And so Bauer's theorem is really sort of implying a version of Gelfand's representation theorem. Okay. Second application I'll quickly mention is to the ergodic decomposition theorem. So in topological dynamics, there's an important functor or passage, if you like, from a flow, which is a compact space with a G action, to the affine flow on the space of probability measures on X. This is a very important process or procedure in dynamics to pass between these two objects. And we say that a probability measure in P of X is ergodic if it's an extreme point of the set of invariant probability measures. So this is a compact convex set. And in fact, it's a simplex. The set of invariant probability measures is, excuse me, is a Choquet simplex. And the Choquet-Bishop-Duluth theorem immediately implies that we have an integral representation theorem of invariant probability measures in terms of ergodic probability measures. So this is the result that was known for a long time before Choquet theory was sort of, I guess, finalized, if you like. It does, though, clean up the proof of the ergodic decomposition theorem. Sort of a much simpler approach than previous approaches to this result. So the third application I want to mention is a more recent characterization due to Glasner and Weiss of property T groups. So I'll gloss over the definition of property T and come back to that because I'm going to mention this again. But what Glasner and Weiss showed is that a group has property T if and only if, whenever it acts on a flow or on a compact G space, the set of invariant probability measures is a Bauer simplex. Now, by Bauer's theorem, this is equivalent to the statement that G has property T if and only if, whenever it acts on a commutative C-star dynamical system or on a commutative C-star algebra, the space of invariant states is actually the state space of another commutative C-star algebra. Okay. So in the non-commutative setting, it turns out that there's a nice analog of classical Choquet theory. It's almost, I think it's surprising how much of the classical theory actually generalizes to the non-commutative setting. And so very quickly, I'll just say that there's a natural notion of a convex function in the non-commutative setting. You look at the graph of the function, and just like in the classical setting, you say that a function is convex if and only if its epigraph is convex in the non-commutative sense. And you can write down a sort of Jensen type inequality, which is equivalent to this condition. So f of alpha star x alpha is dominated by alpha star f of x alpha for all points x and all isometries alpha. And let me give you a more concrete example. If I take a compact interval of the real numbers, I can define in a natural way a compact NC convex set over the interval. Namely, I take the set of matrices, self-adjoint matrices of size n with spectrum contained in that interval. And it's not so hard to see that this forms a compact NC convex set. And it's actually a fact that this is the unique compact NC convex set with the property that K1 is equal to I. And that's because I is a Choquet simplex. And it turns out that a function in C of K is convex as an NC function. And so in the sense I defined above, if and only if, when I restrict it to the first level, I get an operator convex function in the classical sense of operator convexity. And the definition here is that it satisfies a kind of Jensen type inequality where now you're allowed to plug in operators. And this is really, so what I just wrote down, this is really equivalent to an important theorem Hansen and Pedersen, which is a kind of Jensen type inequality for operator convex functions. Okay, so we have all of the machinery to be able to define a notion of non-commutative Choquet order in the non-commutative setting. Namely, we think of a state or an NC state, so meaning a map from C of K into Mn. We say that this represents a point in K, which remembers the NC state space of the operator system A of K. If, when I restrict to A of K, it's point evaluation at X, meaning that mu of A is equal to A of X for A and A of K. So all the definition is exactly analogous to the classical setting. There's a natural notion of convex function, which I just defined. And this leads to a natural notion of an NC Choquet order in this context. So for X and K, we can show, so this is a non-commutative version of the Choquet-Bishop-Duluth theorem, that every point has a maximal representing state. So remember here, we're replacing measures by NC states. So in other words, we're replacing functionals with maps into Mn, with UCP or CP maps into Mn. And it turns out, so the maximality here is in the sense that it's sort of ordered according to these NC convex functions. And it's possible to show that maximality in this NC Choquet order does imply that your measure mu is supported on the set of extreme points in an appropriate sense, in an appropriate non-commutative sense. So things get a little bit more technical in the non-commutative setting, but there is a natural way to say to specify that something is supported on the set of extreme points. So we view this as a kind of non-commutative version of the Choquet-Bishop-Duluth theorem, and in fact, this really is a generalization of that theorem, because if I take points on the first level, this really is just the Choquet-Bishop-Duluth theorem. Okay. And we similarly obtain a kind of integral representation theorem in this context. So if I have a point X and K, and so I can find something that we call a non-commutative probability measure on K that represents X and allows us to write X or decompose X as an integral over our space K in an appropriate sense. So the thing I want you to take away from this slide is not necessarily the technical details of what I mean by an NC probability measure, just that many of the ingredients in non-commutative Choquet theory, or sorry, classical Choquet theory, have nice and natural non-commutative analogs. The rough idea is that an NC measure is a CP map valued measure in an appropriate sense. And by integrating over our space K, what we're integrating over are CP maps, because remember, each of the points in K we can associate or identify with the CP map. Okay. And this leads to more generally an integral representation theorem for C-star algebras and operator systems for UCP maps over these objects. Okay. So as I said, I don't mean to get into the technical details here. This is sort of an advertisement for some of our results. What I really want to get to is this application to what we think of as non-commutative Choquet simplices. So now this is joint work with Eli Shemovich. We say that a compact NC convex set is a simplex or Choquet simplex if each point in K has a unique state or unique representing state that's maximal in the NC Choquet order. So it's an exact analog of a classical Choquet simplex. And the idea is that every point in K can be written uniquely as an NC convex combination of extreme points in K. That's what this definition specifies. And this is really a generalization of the classical notion of a simplex, because if C is a classical simplex, then you can show that there's a unique NC convex set with the property that K1 is equal to C and K is an NC simplex. So actually, it turns out that any such K will be an NC simplex. So this really is a generalization of the classical notion of a simplex. We have, just like in the classical setting, so classically, it's a fact that C, compact convex set C, is a simplex if and only if the bidual of A of C is a von Neumann algebra. This is a result essentially due to Namioka and Phelps. It's really a precursor to many of the results about injectivity of von Neumann algebras and C-star algebras. And we have similar characterizations of NC Choquet simplices. In particular, I'll draw your attention to number 2, which says that K is an NC Choquet simplex if and only if the corresponding operator system has the property that its bidual is a von Neumann algebra. And so operator systems with this property were considered by Kirchberg and Wassermann, and in particular by Kirchberg in his work on the Carr algebra and exact C-star algebras. And they called these C-star systems. And there's also, there's a tensor product characterization that uses, there's a sort of deep theory of tensor products of operator systems that is analogous to the tensor theory for operator spaces. And this was developed by Kaverick, Paulson, Todorov, and Tomford. And we can say quite a bit about the relationship there. Okay. Right. So the point is that there are lots of examples of NC Choquet simplices. In particular, if K is the NC state space of a C-star algebra, then it's an NC Choquet simplex. Okay. So now I'm gonna finish up with some applications. So the first application is a characterization of the state space or quasi-state space in the non-unital case of a C-star algebra. So first of all, we say that an NC Choquet simplex is Bauer, just like we do in the classical setting, if the set of extreme points is closed. And now we were able to show that, excuse me, so in the unital case, K is the NC state space of a unital C-star algebra, if and only if it's an NC Bauer simplex. Okay. In the non-unital case, the same condition holds, or needs to hold rather, for the quasi-state, NC quasi-state space. And in addition, the point Z0 should be an extreme point. Okay. So this gives us a characterization, I think a very nice and natural characterization, analogous to the commutative characterization of state spaces of C-star algebras. Now, there's a very deep and very important result due to Elfson and Schultz that's been of a great deal of interest to people in some parts of quantum information theory and quantum mechanics, where they show or give a characterization of compact convex sets that arise as state spaces of C-star algebras. And it turns out that in order to give such a characterization, you need to specify, in addition to your compact convex set, something that they call an orientation. And this is a way of recovering your multiplication. In the non-commutative setting, our result shows that you don't, so the orientation is sort of recoverable purely from the structure of the NC convex set, which I think is quite interesting. Okay. Second application is to a kind of non-commutative ergodic decomposition theorem. And the idea here is simply that if I have a C-star dynamical system, then there's a natural analog of this functor, which takes a classical flow to the space of probability measures on the flow. Well, instead of the space of probability measures, what we want to do is we want to take the NC state space of the operator system. And there's a natural sense in which this is an affine, we call this an NC affine dynamical system. And the set of invariant NC states on such a system, it turns out that this is always an NC Choquet simplex. Okay? And because of this non-commutative Choquet-Bishop-Duluth theorem or non-commutative integral representation theorem, we get a nice analog of the ergodic decomposition theorem in the non-commutative setting. It says that every NC state can be decomposed, invariant NC state can be decomposed in terms of ergodic states. If your notion of ergodic is that it's an extreme point. And the third application is a non-commutative dynamical characterization of property T. So a sort of extension of this result of Glasner and Weiss that I mentioned in an earlier slide. And so specifically we show, so actually my PhD students, Nick Manor and Sam Kim should also be given some credit, because in 2021, we proved the non-unital version of this theorem. What we showed specifically is that a group has property T if and only if, whenever it acts on a C-star algebra or on a C-star dynamical system with NC state space K or NC quasi-state space KZ in the non-unital case, then the set of invariant states or quasi-states is an NC Bauer simplex. Okay. So in particular, this says that the set of invariant or fixed NC states is really the NC state space of another C-star algebra, typically non-commutative. And as a corollary, we can actually just look at the state space or the quasi-state space in this, even in a non-commutative setting. So a group has property T, if and only if, whenever it acts on a C-star algebra, the set of invariant states or invariant quasi-states is the state space or quasi-state space of a C-star algebra. And the relationship between A and this other C-star algebra is typically, can be quite complicated. It's not necessarily straightforward to write down what this C-star algebra actually is. And this is perhaps another piece of evidence that this dual perspective, so looking at this space of NC states, is actually a fairly natural thing to do in this context. Okay, so thanks again for listening to my talk.
Thank you very much. Any question or remark? Any? Alan.
I have one potential question, which is the following. You see, when one considers classical convexity theory, there is one transformation which replaces the Fourier transform in this framework, which is the Legendre transform, and which plays an absolutely fundamental role in thermodynamics and such things. So do you have an analog of the Legendre transform in your framework?
Yeah, I'm so glad you asked this question, actually. So Efros' student Winkler worked out a version of the Legendre transform for the matrix convex setting. And I definitely agree with you that this is such an important object in the classical setting. I think there are some limitations with Winkler's construction because of the limitations of matrix convexity that I mentioned earlier in my talk. In particular, it's difficult to make a connection to sort of the dual side of operator systems and C-star algebras. So this is something that we're working out at the moment. I'm working out currently with Ken Davidson and my student Adam Humeniuk. We're working out a theory of non-commutative Legendre transform in the context that I discussed today. Yeah.
Yes. I mean, it's good to know in that respect that if you want, there is a beautiful analogy which has been found by Maslow and by the people working in what they call dequantization, which is that they have really worked out the analogy between the ordinary Fourier transform and the Legendre transform. And so this could be perhaps useful in your framework. I mean, this analogy is very, very striking.
Can you please tell me the name of the first?
The name is Maslow and Litvinov. You know, Maslow, the famous Maslow of the index, but also Litvinov died not so long ago. So, I mean, what happens is that, okay, when you deform, if you want, the operations for instance, in the real line, and replace them by what is always present in thermodynamics, where if you want, the sum is replaced by the supremum and the product is unaltered. then what you find out is that when you write the formula for the Fourier transform, you get the Legendre transform. So it's a kind of a limiting case, if you want, of the, and in that way, I mean, they understand convex analysis very much as a limiting case of, you know, holomorphic functions and so on.
Yeah, that's fascinating. Thank you. We'll definitely look at that.
Thank you. Any other comment or remark? Any? Okay. Okay, I guess we thank Matthew again. Thank you very much for the nice talk.
Thanks again for the invitation to speak.
Okay, stay safe and everybody, and we see you next week. Bye.
Bye.